someday you're going to grow up and you're going to leave home and you're going to do what you say.
Probably not. They come back. Really?
It's my Paramedic instructor.
Well, honestly, my plan is to do that kind of.
I just do this before you.
No, that, you know.
I know how to work this, I don't know how to work that.
Between the two of us, we'll maybe
We'll figure it out.
November already.
Whatever else is that.
I don't have that one. Better look. Okay. Maybe I didn't bring anything. Probably right there.
Okay.
Thanks.
Yeah, I help so much.
Hey, dude. Kim Steve. Hey, you've got another day and you haven't answered the articles. And you were first last week. What's going on?
Oh, sorry.
Are you stalkers much or what?
I went to bed last night. Sorry, guys.
You know,
How come you're not worried about me not doing it yet?
because you're old and you can't
Did you
do
make?
I will, just a little slower at it.
it. I know you got to get home and have your wife help you.
Yeah,
I mean, we talked before. So,
Yeah.
yeah, speaking of getting home, my sink and my dishwasher is up there in the house.
I'll get those out for you tonight, okay, leave
Oh,
it.
You gotta be ready to get on that.
And so I texted my wife, I'm like, what's up? I put
The
all my,
house you're staying in?
yeah, I put all my dishes in the sink, and they've been there for 3 days, they're not clean. I'm like, this sucks. So I even set them by the dishwasher, and they didn't.
They still do?
No.
You know what? This morning I'm washing this. I would like to wash this. Day before I get to the house, and when I get back, I'm washing dishes. And all of a sudden I look down and I'm like, oh God, there's a dishwasher here.
I can make this wait 3 weeks now.
So I forgot about that. I hit the button and walk away. Let's go. Next week, if I remember.
No.
That's so
I've got a magic floor. If I leave my socks, they just.
Anything you want there, like this box.
Have you seen that video?
You ever see my black eyes?
Yeah.
Is there a video?
Oh, yeah.
Yeah,
It's a video
it's
way
two,
better
like,
job
it's like these two like British cops or something like that. Yeah.
Oh, I gotta check that
Oh
out.
my gosh, it's so funny.
Well, my wife did laugh at first.
Black Rifle Coffee Company. It's like they do these like funny videos. And he did one about his broken dishwasher too. He's like, my dishwasher, and it's he's calling his buddy. And he's like, what's going on? I don't know, man. I haven't done anything. He's like, well, I think it was like, can you like do it on like a video chat? And watch over and just watch this.
And then I have a different screen for on stage.
Oh, golly.
Yeah, it's,
Let's get some orders.
What?
Let's see orders for section. Files.
oh, no.
I need to make
Do it at the end of the week.
I don't know, are we supposed to fill it in, or are we just supposed to?
I think we're just testing all.
Yeah.
So it's up to you how you make your card, or even if you just want to study them. But it's 7 or 8 that we're doing.
Yeah, I'm just gonna look at this. Thank you, Bob.
That's based on. And then there's this great part that I went to Seattle with, but it's called acidosis. He's such a nerd, but it's so helpful.
Is that like online or something like that?
It is, yeah, some podcasts, I don't know.
Acidosis.
Acidosis radio, and it is long. Like you can get 2 parts done if you don't come from Seattle. It's pretty intense because it's a bunch of normal. It's advanced. No more.
Oh, flight ranking.
Yeah, according to some stupid.
Yeah, it is. He just has it. Yeah, that's it. Yeah, that's for you. You can move your brain. There you go. It's about
But you know what? He's like the next person of the king. I'm like a 60.
Right in the middle of the
Exactly.
fire.
I want my casino. Drop this.
Flashcards.
Are you slide for access?
Well, yeah. Yes, that's it.
Get it up for long.
Everyone's being shared. Oh, I am actually gonna do that.
Is there anything with the accident?
No, that's illegal.
Yeah, that's what I'm doing. At least that's what I'm asking.
So it's just 5 points. One go to the next category and
First.
Wednesday.
Yeah. Well, I switched it over because we didn't risk 27 yesterday, so. Oh, it's looking like four. From home.
You're doing that second day.
I guess we just do
Maybe it wasn't.
It's Wednesday, right?
Sounds like it's a.
Yeah, there wasn't very much in it. I didn't reference the area, reference the going
But that's just. What days you work this weekend? I mean, about working on Sunday. But like, no, that's, oh, yeah. Oh, yeah. Oh, yeah. Oh, right. Yeah. Yeah. Well, and you know, the things that I really appreciate. You know, and the thing is, but while you're talking about my, you know,
I thought you were maybe having
yeah, no,
yesterday we talked about electrolytes, yes? Okay, good. Get me started. Tell me about it. Tell me her. I got paid.
They help me with electrical production.
Thank you. I'm going.
cation, anion,
What's the difference?
positive, negative.
Charged. So name of the cation ion. Calcium, good. Magnesium, good. What? Potassium, good. What's another one? Sodium being the big boy, right? Okay, keep going. Where are you going to go on there?
Each cation has an anion to balance it out.
That's supposed to dissociate, right? Yeah. Good. What else did you hear?
Hypertonic, isotonic.
What's the difference?
Hypertonic is when the solution outside the cell is positively it has to do with osmosis, and so it's going to be positively charged. So it's drawing the sodium out from water moles, sodium.
Okay. We talked about water, yes? What's the deal with water? You're supposed to solve it. Good.
Yeah.
Yep. Good. So you and I, as we're sitting here, have a total body weight of how much you drink. So what's the breakdown term of that? Where's the weight at? 45% is in what? Intracellular, 15% is extracellular, and there's a further breakdown, extracellular being 10% of being where? Interstitial. Okay. And about 4.5%, 5% of being intravenous. What else?
Aside from the eagle line, so again, we talked about the semi-permeable ingredients.
So Christina, tell me about that semi-permeable membrane.
Some molecules are too big to cross it.
Yeah.
I mean, they need a helper protein.
Yeah.
And some of them are small enough that they can. And then we talked about passive transport.
We did. We did. You weren't dreaming that. We did.
It's all melting together.
Yeah, exactly. This isn't scary though. So while we're in that neck of the woods, we talked about the fact that the semi-permeable membrane will allow some things in and other things not. And that's kind of what you said. What's diffusion then?
That's the process of the molecules crossing that membrane and spreading around.
Okay. What crosses it most actively, solutes or solvents? Solutes, right? So an area of higher concentration to an area of lower concentration. And so osmosis then is what?
The diffusion of the water.
Does it go in the same direction as diffusion or opposite direction as diffusion? Opposite of diffusion, right? So why does that matter to us? So what?
You have an electrolyte imbalance. That's caused a lot of issues.
Yep, that's part of it. What else? As you're sitting here, is osmosis and diffusion taking place in your body? Right? So the idea of the coffee that you're drinking right now is going to result in something going on with osmosis and diffusion. The Coke that you're drinking is going to have a difference in terms of osmosis and diffusion. So it's an ongoing type basis in terms of homeostasis, right? What's the osmotic gradient?
The flow of the water or
What about it? Absolutely. So the idea when there's a difference on one side of the cell versus the other side of the cell, right? And so it makes it up with isotonic, hypertonic, and hypotonic. What's isotonic? Equal on both sides, right? When we give an IV fluid, what are we generally giving? Isotonic solutions, right? And so it equalizes. What we talked about earlier in terms of isotonic fluids that we give as an IV. What happens to it? Crosses and they do its thing, and 2/3 of it is gone within an hour or so, right? Christina, you talked about passive transport, doesn't require any energy. What is active transport? Requires ATP. What's ATP? Or energy source, right? What's facilitated diffusion?
you have transport molecules that grab onto the thing that needs to go across and helps it across.
What's a good example of facilitated diffusion? Insulin, good. So when we do end up having issues on one side, as in, i.e., we're either dehydrated or we've got too much fluid on board, what does the body do in terms of response to that?
Produces hormones. So either the ADH hormone.
Yeah, cool. So ADH hormone, what's that all about? So what does it do? So the kidneys hang on to urine, okay, or hang on to fluids, I should say. And so when would that happen? What state would that happen? Dehydration, right? So what happens if we happen to be overhydrated? We had been drinking water all night long. What would be happening in that state?
Opposite.
We're pitting it out, right? And so the idea in terms of osmosis and diffusion takes place in that as well. But the kidneys are the organ of function as far as making that happen along the way.
Is there a diuretic hormone, or is there just
All by itself? No. All right, cool. So the reason I start this lecture with that review is that everything that we talked about yesterday falls into what we're talking about today, and that is acid base. How many of you consider yourself to be good with acid base?
getting there?
Right there, right back there. That's a specialty today. That's his thing. He can get up and teach this very easily along the way, but he's not using the sequence. The rest of you, where are you at with it? Have you ever heard of that before?
Yes.
You've at least heard it, at least in distance, right?
I read about it this week.
The holiday in effect. What else? What else can you tell me about it?
Henderson Aquabach.
Say again?
Henderson Aquabach. I don't know if that's but there's the formula for calculating the pH.
You already heard me this morning. Okay, yeah, you're right.
Man, we're supposed to know that coming into class. I'm screwed.
What else? Can you tell me, folks?
Our body has a pH of 7.5 to 7.45, and that we would try to maintain that level through our lungs.
You're already got a foot into learning about this. If you know that, then you got a foot into it. Right. What else?
It's,
As something flames, the body reacts and tries to set that equation.
In an opposite direction, right? And again, that's the confusing part of this. Acid base is always confusing because it moves in opposite directions from what you expect. So never it's moving one direction. What the body's doing is moving in the opposite direction, right? And that's kind of confusing along the way. That's where we'll spend some of our time this morning. What else can you tell me about it?
the pH, PCO2 trend together in a metabolic state, and if it's a respiratory issue, then they trend opposite.
Okay, we'll talk about some of that.
The 0.5 is how much it can differ where your body doesn't want to sustain at that level.
Okay.
And yeah.
Okay, so you're saying, yeah. Good. What else can you talk about? So as we live here right now, as you're sitting here right now in this classroom, are you slightly acidic or slightly alkaline? Slightly alkaline, and we're talking about that, okay? It's a necessity for it to be in that slightly alkaline state. Okay? What else can you tell about it? That's not a bad start. Let me tell you, as compared to past classes, you're already just a wee bit higher than we were done before. So hopefully we're getting as well. So here's my other thing for you, is that we ever spend the morning talking about this and nothing about this. Okay? So I will slow down, I will chill. If you do not understand something, it's you that you keep your hand up and say, dude, I don't get this. Okay? And we'll go back and do it again. Okay? Now I got to help this class with respiratory therapists to come alongside you today. Okay? And so the whole thing about this is if you want to get really, really deep into this, which you easily can, we're not going to do that. We're going to go just enough so that you understand the basics of what happens with acid base. But if you want to get a wee bit on the deeper side, there's all kinds of reading out there to get there. Okay? That's so level on what happens in aerobic, anaerobic metabolism, and that whole thing. Okay? There's plenty for you to take a look at if you want, if you're interested in this. Okay? So I have to tell you, I have to confess something to you about this. Years and years ago, I hated this topic. Hated it with a passion. For the same reason you're doing to hate this as well. Okay? The idea that it's hard to get your head around, the idea that it's hard to understand along the way. And so my whole thing was that I didn't understand it at all. And one day, there was like a epiphany that came on that actually started to make sense what we're doing. My hope for you at the end this morning is that at least there's an understanding in terms of the different processes along the way and why it makes a difference to you. What we're talking about during this lecture is you don't have an acid base, or you don't have an arterial blood acid before you. That guy does. So he knows the terms of numbers and things like that. You're not going to have that advantage. And yet it's important for you to understand this for the reasons that we're ready to talk about this morning. Fair enough? So that's my starting point on this whole thing. So we are going to talk a little bit about the basics. We're talking about the body regulation acid-base balance. We'll talk about three different portions the body uses to maintain this in a real tight range. We're going to talk about some normal values. You already told me about the pH of 7.35 to 7.45. We're going to talk about a couple other values as well. We're going to talk about four main acid-base arrangements. We're going to talk about metabolic acidosis, respiratory acidosis. We're going to talk about the alkaline state as well. And then finally, we're going to do a little bit of scenario playing. So we kind of established this yesterday. We talked about ions, but more specifically today we're talking about hydrogen ions. So it's a molecule that's lost its lone electron, and it is a proton. So remember yesterday we were talking about an ion can be positive, can be negative, or can be neutral in the way. All this is saying here is that this is primarily a proton. Substances that give up protons during chemical reactions are considered to be acids. So there's acid and there's base. So in this case, we're talking about a hydrogen ion that's considered to be an acid. Hydrogen ions are produced mainly by glycolysis. What's that? I hear a lot more.
Breaking down sugars.
Thank you. So the idea in terms of breaking down sugar, where does it primarily take place?
Liver.
Liver. So what happens if somebody has cirrhosis? How well is it going to work? Not well, right? So the idea in terms of certain disease states already set this up, and we have problems along the way. And that and a whole lot more that we're talking about this morning. Substances that acquire protons are considered to be a base. Hydrogen ions are part of ATP production. We said that was what? Energy source, right? And so we talked about a number of other reasons for energy source yesterday, one of them being glucose, right? But if you think about what we just got finished talking about, this right here has something to do with glucose. This right here, then, is the end effect that is going to do something with glucose along the way. Okay? So if you're extremely acidotic, your glucose is going to be in danger one way or the other, either low or high. So it's not just acid-base all by itself. So as we tie back into yesterday, one function of electrolytes is to form acids and bases. So remember we were talking about those anions yesterday, and that they play a part in terms of acid base. This is what we're talking about right here. Bicarbonate being the big point. Bicarbonate we're talking about when acids freely give up hydrogen ions, and bases freely accept hydrogen ions. This is the key concept right here. Acids freely give up hydrogen ions, and bases freely accept it. So this relationship between acids and bases is back and forth and back and forth. And these two work together. Sometimes they work apart as to how well that it goes or not goes along the way. And so there's 20 bases to every one acid. 20 bases to every one acid. So that being said, the bases are going to try to keep each acid in check along the way. So when we talk about an acid-base imbalance, we're talking about the fact that this relationship is not real great between acids and bases. pH is a measurement of how many free hydrogen ions are available. Hydrogen ions are acidic and must be maintained. So that's the second time already that you've heard the fact that this is about acid. So hydrogen ions are acid. Any major deviations adversely affects the biochemical functions of the body. So the idea that once we become in an acid state, acidotic state, once we become that way, the idea doesn't take a whole lot to tip us off the edge. So while we've already real early on talked about a pH of 7.35, 7.45, all you have to do is be down to a pH of about 7.15 to be in cardiac arrest. Okay? So it doesn't take a whole lot of the scale of sliding back and forth to get in trouble. And that's not what we'll be talking about. Are we okay with this? Do you understand this? Ready to stop? Go back.
I guess if we're in a more acidic state, how does that person into cardiac arrest?
Not all by itself. So it isn't the acid producing that cardiac arrest. It's the result of the cardiac arrest.
Oh.
So it's the other way around. Okay? So we'll come back and talk about that. You said something about 20 to 1. 20. Hang on that because we're going to come back and talk about that as well. But as a starting point, 20 bases to 1 hydrogen ion. Okay? So the idea that we're trying to keep that hydrogen ion in a close proximity, it's going to take 20 to 1 in order to do that. And we'll talk about why that is. Okay?
Does that mean it takes 20 bases to overcome one acid?
It just is regulating it along the way. That's all it is. It's keeping it in check in terms of regulating it along the way. Okay? And the whole reason for it, I'll throw it out now, and again we'll talk about it. That is, this turns into carbonic acid. That is, that it engulfs the hydrogen ion, if you will, dissolves it, and it's gone. That's why it takes so much base in terms of pulling in each one of the hydrogen ions along the way. Okay? And so it's there and it's gone. We'll talk about how that plays out with the body system. Okay, so this is the part that kicks folks, and that is that pH is inverse logarithm of the hydrogen ion concentration. The greater the amount of acids, the pH goes down. Okay, so let me put it up here this way. Okay, this is part of what kicks folks as far as this whole process. This scale, and I'm not talking about a scale in terms of arterial blood gas. I'm talking about a scale of you and I and all the stuff that we take on a daily basis goes from a 0 to a 14. 0 being a very strong acid, 14 being a very strong base. The lower the number, the greater number of hydrogen ions. So again, 0 strong base, 14 strong, 0 strong acid, 14 strong base. So if we're talking about something with an acid of 1 and 2, very, very strong along the way. And I'll show you, it's in your slide presentation already, but I'll show you in the next slide how this kind of balances out between the two. Decreased number of hydrogen ions. So the higher the number, the decreased number of hydrogen ions available. So if we get it into a 13 or 14, a food product with a 13 or 14, there's very little hydrogen ions are associated with that. So acids have a pH less than 7. Bases have a greater than 7. So 7 is considered to be neutral. If you were to take distilled water and you were to pour it out and you were to measure it in terms of pH, it would be 7. Okay? Number ratio of carbonic acid is 20 to 1. We've already talked about that. The idea that 20 base to 1 acid. Josh, you okay so far? So here's a scale. You don't need to remember this, but I just want you to take a look at it. So put your pen down for just a second and look at it. So what we're talking about here is we're talking about products out there. We're talking about some food products out there. We're talking about life out there that are strong on the acidic side. And we said this is neutral, right? Distilled water right here, okay? So going from 7 then to 14 is all about base, okay? So look at the products, look at the processes in life, okay? So let's go to 1, stomach secretions. So if you got an upset stomach, if you happen to have heartburn along the way, what do you take? Tums. Let's take a look at this. What do you find Tums? Base, right? So for every acid that's out there, we can take something, not always, but we can do something in terms of trying to neutralize that. Okay? So stomach secretions, Tums. What does Tums do?
Neutralizes stomach acid.
So yeah, you're right, but how does it do that?
Lowers the heat.
Essentially, it's doing exactly what we talked about with base. Absolutely. It's creating its own in terms of base that's going to neutralize the acid. Does that make sense? Okay. So check this out. If you're drinking a bunch of Coke or Pepsi products, high in acid, right? And you probably have seen or read something about the fact that if you take Coke and you put it down to a grain, it's going to start bubbling and cleaning it out and everything else like that. That's what's happening here. So what happens to you in terms of drinking a bunch of Coke and Pepsi products? Does that mean that we're going to die? Probably eventually, cancer, I don't know, something else along the way, right? But then what happens with the body? How does the body respond to that? It's going to start kicking something in terms of bases. So if you happen to be drinking Pepsi products all day, every day, your body will get to a point where it's going to struggle with trying to take care of you with that. Okay? on anything about Coke or Pepsi products, but that's what it does, how the body responds to it. So I find this interesting as well. So vaginal juices are high in acidity. Why?
It's help with cleaning.
So about infection, right? So the idea in terms of urinary tract infections in females is very, very hard to test it, right? So one of the reasons of the way the body responds in the female is the fact that it's going to have a lot of acid. So if that's true, then how is it that any female can ever get pregnant? Because they have to be high on acid. That came out wrong.
I feel like that's
So I think that's what happens to me.
Try that again. That is that in vaginal juices that it's high in acidity, okay? But check this out as well. How is it that you can ever get pregnant based on the semen being on the base side? So the idea that if you look at it, this is closer to a neutral thing, and this is somewhere in between in terms of between acid and neutral base. So the idea is it isn't that it can't, it isn't that it won't, obviously, but the idea in terms of for every acid that's out there, there's either things that we can do for medications, or there's things in terms of how the body responds to try to bring that back into its total homeostasis effect. Does that make sense? And so again, it's no different, folks. It's no different the way our body works as far as between this acid state and this base state. Okay? Can I go forward? So whether the blood is acidic, neutral, or basic depends on the concentration of dissolved hydrogen ions. Remember this being an acid. The more the hydrogen ions present, the more the blood will show as an acid. The lower the amount of hydrogen ions, the more the blood will show as a base. So later on, as we start talking about the derangement, we talked about an acidotic state versus an alkalotic state, that's how it shows up. So Josh is in his shop, and he's looking at a arterial blood gas machine, and he's looking at the different states between this. What he's really looking at is the fact of this balance right here between too much acid or too much base. Normal homeostasis, you and I, as we live and breathe every day, normal homeostasis attempts to keep a tight range and concentration of hydrogen ion by using a narrow range of the pH scale. And again, I said it once, I'll say it again, I'll probably say it a number of different times this morning. It is a tight range in terms of 7.35, 7.45, and anything outside of that is considered to be a problem area. Acid is considered to be a normal waste product. It isn't like it's bad. It isn't like you got acid in your base. I need to do something about dissolving that. It happens all by itself. And in the process of back and forth, across the cell membrane. The pH in the body is a balance between the amount of acid that is produced and the amount of acid that is eliminated from the body. Where's it eliminated from? How does it eliminate? Urine is one thing. Breathing. Respiratory side is the other side of that as well. And there's actually an internal buffer that we're talking about as well in the third way that happens. Body fluids must stay within the pH scale to prevent disaster from your patient. Check this out. pH above 7.45 is called alkalosis. pH below 7.35 is considered to be acidosis. You know that. That will come back. Not just for testing. You know that in terms of how this whole thing works. Slight change either way in the pH scale can be devastating. It doesn't take a whole lot to get back. Are we okay? Can I go forward? Yeah.
So the acids freely give up their hydrogen ions.
Yeah.
Bases want to collect them.
Yeah.
Is that because all these solutions are trying to be neutral?
Pretty close. So it's trying to remain in a homeostasis state. So yes. Okay? An acid is a substance that increases the concentration of hydrogen ions and water. So the idea that the more acid there is, the more that's going to be dissolved within a water solution. So the more hydrogen ions, the lower the pH, acidosis. The less hydrogen ions equals the higher the pH, alkalosis. So that goes back to exactly what this is right here. The more acidosis that we're talking, or the more acidic the body is, the lower the pH is going to be, and vice versa with this right here. Okay? So as we start talking later on about acidosis versus alkalosis, then it's coming back to us right here. So we said that pH of 7.0 is considered to be neutral, distilled water along the way. We've already talked about the fact that our normal pH for us as we sit and live and breathe here is 7.35 to 7.45. So max range of pH less than 6.9 or pH greater than 7.8 is considered to be compatible life. 6.9 greater than 7.8 is compatible life. pH of greater than 7.45, we said is alkalosis. pH less than 7.35 is considered to be acidosis. Now, as we talk later on, we'll talk about somebody that's in cardiac arrest, and we'll talk about the fact that this pH will fall in a huge way depending on what all is going on with the cardiac arrest. But it is not at all unusual for you to resuscitate somebody, especially somebody that has been down for an extended period of time, and you get into the hospital, you might get lost back along the way. You get into the hospital and they pull off arterial blood gas, and they've got a pH of 7.05, 7.0, which is right on that edge in terms of how well it's going to turn out. It gives folks at the other end that's looking at a machine, it gives them a clue in terms of how severely acidic they were along the way. Yeah? Yeah.
Just a side note, how long does it take for that to develop?
Sometimes very, very quickly, sometimes over a long period of time. So let me give you an example. A CHF, for example, where they've been chronic, getting worse over a period of time type of thing, their pH over a period of time will start sliding into a more of an acidotic state. Versus somebody that has a major trauma and they're losing a bunch of blood into their pelvis very, very quickly. So it just depends on what the disease state is, what the injury is that kind of defines it. Make sense?
Yeah.
Okay.
Now, is that because a CHF patient can't expel a lot of that CO2?
That's part of it. Yeah, that's part of it.
Okay, what's the name?
The thing is that CHFs live with us every single day. Okay, so the idea is it's kind of like the COPD being the same thing. They live in that state every single day. And so while you and I live with a 7.35, 7.45, they're probably right on the edge of being like 7.25, 7.3 or something like that. The body gets used to living in that state. Okay? And so, again, it doesn't take a whole lot to go from there to there on the sliding type thing. Okay?
Does the body start to compensate?
To a certain degree it does. It never does great in terms of living outside of this range that we're talking about, but to a certain degree it does. So, like I said earlier, it's not that acids are the bad name in town. The idea that it's a normal metabolism, you can't live without acids, you can't live without base, the idea that it has to deal with the normal range. So a constant hydrogen ion production equals a constant pH regulation required. So again, the base has to do its job as far as dissolving these hydrogen ions as they go. If they don't, then we become acidotic over a period of time. Sometimes short, sometimes a long period of time. So one of the big things we need to talk about is the body utilizes 3 different systems to help regulate this acid-base balance. You need to know that the buffer system is part of this. You need to know the respiratory system is part of this, and you need to know the renal system is part of this. Okay? And we'll look forward, we're going to break those down and start talking about it. Okay, so put your pen down for just a wee second. Go down. You need to know this formula. In part, not because of some tests that we're moving for you, but you need to know this in terms of understanding what we're talking about, okay? So let's walk through it together, and then you can do whatever you want as far as your notes along the way. So on the left-hand side, you've got hydrogen plus CO2, water, and carbon dioxide, yes? You've got in the middle this H2CO3, which is nothing more than carbonic acid. On the right-hand side, you've got the hydrogen ions, and you've got the bicarb that makes up this side, okay? This formula must remain in balance in order for us deliver mud. Okay? And it does. The idea that this right here, this carbonic acid, is the net result of the base versus the acid. Okay, of breaking that down. Okay, so as we start talking about the first system, which is going to be this buffer right here, the idea that this is the first game in town in terms of trying to keep everything in balance. Okay, so that balance of 20 to 1 is all about the breakdown of this right here for making this happen. So I'm not going to ask you about this formula. I'm not going to put it on the test in terms of what this formula is, but you need to understand which way we're going. So to that, the other way of looking at this, I don't want to get ahead of myself, but the other way of looking at this, if you look at this H2O and CO2, what system does that remind you of? Respiratory, right? What does this remind you of right here? Metabolic or kidneys. So remember we said that there's 3 different systems that's part of this, right? We talked about the buffer system, or we will talk about the buffer system. We talked about the respiratory system, and we talked about the metabolic side or the renal side. If you think about this formula in terms of what's going on back and forth and back and forth and back and forth, in my pea brain, the way that I think about this, the way I remember this, is the fact that on one side we have a respiratory system that's a portion of this, on the other side we have kidneys portion of this, in the middle we have a buffer that's trying to maintain all this. Okay? Let me put it even more simply that hopefully you understand. I think about this as being a fulcrum or a ketone. Okay? And there is pea brain, this is the way I think about it in terms of bouncing back and forth and back and forth and back and forth along the way. Ongoing type process. So on the left-hand side, we've got the respiratory system that's going to balance out with the renal system that's balanced out in the middle with the buffer system. Okay? I'll shut up for just a second, and then we'll come back to it.
That formula, is water and carbon dioxide come together? What are those arrows?
Then they go back and forth, back and forth. So this goes back and forth across the scale.
So where does that carbonic acid at?
Carbonic acid right here is this right here. So the buffer, the 20 to 1, the so-called 20 to 1 is the breakdown of this right here.
Where does that happen?
Oh, it happens without the throughout the system. So its hydrogen ions are produced more and more and more. The buffer system will then go in and try to absorb it like a sponge type thing.
We look at the H2CO3 in the middle.
Yeah.
So on the right, we have an H2O3 and an H. So if the 2 H's together, you have H2CO3. So when those 2 meet, they become carbonic acid.
Is this happening in blood?
Yes.
Okay.
So we talked about it earlier, it was the part of glycolysis, or cell that's doing signal glucose, trying to make it, byproduct is that H+. So throw it out those H+ ions all the time, and then the bicarb that's picks those up, becomes carbonic acid. Then it sits in the blood as carbonic acid, and it's lungs, they separate. They have the H2CO3 and separate into H2O and CO2, which is just water and carbon dioxide. You let the carbon dioxide off, the water stays in your blood, or also gets blown off in the water. So the byproducts end up being 239.
Okay, thank you.
Make sense?
Yeah, and then in the other direction, how does that?
Well, it wouldn't necessarily be going in the other direction. You're not adding water and carbon dioxide to your blood all the time. But as they sit in the blood, so let's say they didn't leave the body of the lungs, they stayed in the blood, they're going to continually form that carbonic acid again. And kind of go back and forth. That's what chemistry is always doing this. They're breaking and connecting and breaking and connecting. So they're just going to wait until they get back to the lungs again.
Okay.
So the other thing about that, going along with what Josh is talking about, it isn't like we have this water all by itself. But these two go together in terms of the way that it works. And so that's the portion that gets expelled through the lungs. That's a portion that gets expelled through the kidneys as well. Yeah.
Just think about the blood always has all of that in it. It always has the water, carbon dioxide, the carbonic acid, the H+ and the bicarbonate, different quantities. But as you get more of one thing, they're going to start to separate more off on this side, or they're going to start to unite more on this side.
So part of it that when you have cellular respiration and that cell is kicking out CO2, it's meeting up with water in the blood, and so then we're creating the carbonic acid right there.
It's actually not kicking out CO2 anymore. That's what you think of. It's kicking out the H+ ion.
Okay.
They're connecting to the HCO3.
Okay.
The bicarb. That's converting to carbonic acid. Then those two separate into water and CO2. So it's not that we're producing CO2 in the cells, it's that we're producing the H+, which ends up becoming CO2 in the molecule.
Okay.
So it becomes like a waste product that you already know about in terms of CO2. Yeah.
So where do we create bicarb?
Where do we create bicarb?
Yeah.
It's sitting in our body all by itself. So remember one of the anions we talked about yesterday is bicarb. So it's abundant in the system.
Okay. Our electrolytes.
Yep, exactly. Okay. So you need to know these numbers, okay? You do need to know these numbers. And that is that that pH we talked about already being 7.35 to 7.45. PaCO2 is 35 to 45. As we move forward, as we start talking about capnography, as we talk about the effects of capnography and everything else like that, that's the number of these three. That's the number that you will be most exposed. So 35 to 45.
So when we're reading capnography, we want to see 35 to 45.
Absolutely, absolutely. So this number is just a wee bit. Let me tell you about it. So depending on which book that you're picking up, and I'll ask Josh's opinion here in just a second. The normal HCO3 or bicarbonate ion is 22 to 28. You'll read in some textbooks about 22 to 26. So the number that generally will work with is 22 to 26. Josh, or
Yeah, I always learn 22, 26. Like the Sacred Heart, our normal values are like 23 to 27 actually. So it's kind of like weird.
and so it's all over the place. I don't care that you remember the either 26 or 28. I'll work with either one. But generally 22 and 26 is what most people will say.
That's way to remember that. Just remember 24. Just remember
Yeah.
It can go down
Yeah.
by 2 or up by 2.
Yeah.
24 plus or minus 2.
So check this out. I've already talked about it, but I want to hammer it. And that is that H2CO3, this right here, doesn't hang around for very long. It will do its thing in terms of attacking the hydrogen ions and will dissolve. It dissolves in carbonic acid. Where does it go from there? Where does it go from there? Lungs, right? Where else does it go? Right? We're specifically in a renal system. How does that work in a renal system? So we talked about, remember we talked about ions being given up and everything else like that? That's this right here. That's this right here in terms that the whole nephron, the way that it works with convoluted and visco tubules along the way. It kicks it off with this right here. Okay? All right, that's a good place to stop. Stand and stretch. And I'm going to be short break this morning for the content of what we're talking about. Come back in about 5 minutes.
Gary?
Yeah.
Carbonic acid, in fact, that doesn't stay this very long because as soon as it hits the lungs, it's kind of separates and then we blow it off.
All right, let's go. So, as a short review, tell me where we went in this first hour. Where did we go in this first hour in terms of the starting discussion? Remember that much. I'm not encouraging you, folks. What about it?
Produced by breaking down sugar in the liver.
Okay.
And then that gets turned into, well, the sugar gets turned into ATP, and then you get these extra hydrogen ions that are floating around as the waste product that creates the acidic state.
So, okay, go ahead.
We are
What's the balance to the hydrogen ions we talked about?
bases.
The base, right? And so there's how much base has each hydrogen ion? 20 to 1, right? So they keep this tight rein on it as far as keeping the acid in check. Okay? What's the normal pH for us that we live with? If a pH is 7.25, is that acidic or alkaline? Very good. So what's the normal range for PCO2? maintaining for HCO3? 26 or 28, either way, right? Okay, so I won't get that particular. So the three systems that we talked about, we're going to talk about further, or what? That regularly. And the buffer, right? Right? Any questions that first hour? Yep. Is that a hand?
Well, I'm curious.
Curious.
I don't want to confuse myself, but so if we go below that 735 and 7 is considered neutral, wouldn't 725 still be alkaline?
No. It's alkaline in terms of the way the scale talks.
Okay, but as far as our body's concerned.
But as far as you and I being compatible with life, no.
That's nice.
Good question. Anybody else?
So when ATP is produced, byproduct of that reaction is the HCO3. Or is that
Byproduct ATP.
No, we were just kind of looking at that. So we were talking about, so there's different energy sources. You have aerobic metabolism and anaerobic metabolism. Glycolysis is actually breaking up those glucose molecules, and that actually produces pyruvate and proton are those plus molecules. So during glycolysis, we're breaking those sugars out. And then when you actually go into the Krebs cycle, that's when you're actually producing some carbon dioxide as well. So you got both rolling into the mix. But you kick out hydrogen, and you're taking out carbon dioxide, and they want to attach to something. This is what they're doing. Forming together with the HCO3 bicarb. That's something that your body's just producing as a bloodstream.
All by itself.
And your kidney is regulating.
Okay.
So it's not a byproduct, it just constantly is produced along the way. Okay. Anybody else? All right, so let's go. Take some new territory here. First of the three systems is a buffer system. So remember, it sits in the middle. It's that here quadrant. I don't want to use the word attach, but it's essentially what it does. It helps engulf the acids to keep it within that regulated 20-to-1 ratio. First in this acid is the pH regulation, also considered to be the weakest of the three. So it does its thing. It chews on the pH, or excuse me, it chews on the hydrogen ion, and then it's dissolved into a carbonic acid. It maintains this ratio of 20-to-1. When the ratio is lost, bicarbonate seeks to soak up the hydrogen ion. So the more acidic that we are in our body, the more the buffer system will try to maintain along the way to keep this ratio. Okay? What happens when it can't? What happens when our body is overwhelmed with an acidotic state? So there are other systems, and so this is short, it's acting, it's fast, it's like the first attack, if you will, for whatever's going on with acidosis. Okay? But it's not the only one, unfortunately. It would be dead if it were the only game in town. When the body believes that pH is less or more than normal, the buffer system will either give off or take in bicarbonate ions. So to this point, we've been talking about the fact that acid is always the big thing, right? What happens when they're in severe alcoholic state? Too much base or too much acid? Too much base, right? So what do the hydrogen ions do? They will rise up in the fact that they're not going to be engulfed by the carbonic acid. Instead, they're going to try to balance in terms of the body system of maintaining that acid state, or excuse me, maintaining enough hydrogen ions, I should say. Let's say there are too many hydrogen ions in the body. The body will release bicarbonate ions, HCO3, to bind with the free hydrogen ions and thus make up carbonic acid. Carbonic acid becomes a waste product that's expelled either through the lungs or through the kidneys. This carbonic acid easily breaks down into carbon dioxide and water as we move through primarily to the respiratory system. So the second of the system. The second to kick in, it kicks in this order right here, is that respiratory system is there doing its thing for 2 to 4 minutes. So how does the respiratory system say, you know what, I'm tired today, I really don't want to do my job? How is it the respiratory system finds out or starts doing its thing as far as doing this? Absolutely, that's part of it. What else? Ready, right? Remember we talked about negative feedback a long time ago? The idea in terms of negative feedback is it's really what's going on. Or positive feedback depending on which state we're in. Okay? So the brain's part of this. CO2 is part of this. Are there receptors along the way that's part of this in terms of regulating this process? So it is. Say again?
Well, I'm sorry, was it the chemoreceptors?
Yeah, chemoreceptors and baroreceptors, yeah. So it isn't like this just lives in this own little vacuum, right? The rest of the body is part of this as well. I don't want to exclude that because we'll focus on this right here. Take 2 to 4 minutes to start to work and then kick in. And the whole thing about it is going to eliminate or retain CO2. Depending on what state that it's in, it's going to eliminate or retain CO2. Kicks in and the buffer system is not able to maintain the ratio of hydrogen ion concentration. System speeds up or slows down to maintain homeostasis. So let's kind of walk through this. You have somebody who has overdosed on heroin. That could be an acidic state or alkaline state. Well, respiratory system is slowed down. What's going on with the CO2? Is it being expelled or retained? Retained, right? So the whole idea behind it is that it's retained. What you're going to come in, you're going to do your hero thing. What are you going to do? You're going to get the Narcan, and what else are you going to do? You're doing exactly this right here. You're correcting the state. That's all it is. Okay. Same thing on the metabolic side. What's the reason for a metabolic acidosis? We're early, and we'll get there in just a second, but what's the reason for it? Check. So just for example, we'll paint it this way. You're on scene of a major trauma to where they have a pelvic fracture, and you know with certainty that they're bleeding into the pelvis. Okay? Is that going to be an acidotic state or an alkalinic state? Likely to be a what? Acidotic state. So if you think about this formula, back up to this formula for just a second. If you think about this formula, the system that's going to be affected right here is this right here. What is the respiratory system going to do in trying to compensate for that? Speed up. Because it's going to get rid of the CO2. It's then going to say to the renal system, I'm going to come alongside and help you as much as I can. Okay? And so the idea in terms of acidotic state, these three systems all work together in terms of how they're doing that. Okay?
Why is bleeding out into your pelvis an acidotic state?
Because it's a shock state. Okay. So it's hypervolemic shock at fine, right? So anytime that we're talking about a shock, and I don't want to get ahead of myself, but anytime we're talking about a major shock, the metabolic side is bound to be affected by that.
The reason is because you switch from aerobic
There you go.
anaerobic metabolism to produces lactic acid.
And that's where we'll camp just a little bit. So
Let's go back to that heroin thing. Why did we say it was acidotic?
So because it's retaining CO2. Okay, so that 35 to 45 CO2. Yeah. Yep. Yep. So lungs aren't functioning the way they should. Right. The way that we're going to correct that is Narcan. The way we're going to correct that is respiratory side. We're going to speed it up to blow up that CO2, and that teeter totter comes back into a balance again. Right. I got that.
So, and then your other example, the reason we tell a patient with rapid respiration is because he's trying to fix that.
All right. So let's say too many hydrogen ions in the body, acidotic state. The body will release bicarbonate ions, HCO3, will bind with this, and it goes on and on. Okay.
So here in that last slide says it takes 2 to 4 minutes to start the work.
Yes.
Isn't it constantly doing that?
It is. It's just that it takes 2 to 4 minutes for the message to go from here to the baroreceptors to the lungs in terms of doing its thing. The lungs will continue doing its thing, but
if you get into acidotic state.
Right. It just takes a wee bit for the message to be there for that negative feedback cycle. That's all it is. Right? It isn't the lung stop working, then suddenly you start again. Okay. A decreased respiratory rate for someone breathing so shallow as to not be able to blow off CO2 equals increased CO2. So let me say it again. The example I just gave you was about the heroin overdose. The respiratory rate is about 5. So CO2 is sitting there in the lung, it's not being blown off, it's just kind of sitting there, right? Which is not healthy for life, right? Would you say that if we were to hook up Mankato, would you say that the PCO2 would be high or low? High, because it's maintained. Remember, it goes in opposite direction. Okay? So if you think about that formula, that's what's happening here. Okay. So we're talking about respiratory system that's either slowed down significantly, so retain CO2, means that the metabolic side is going to try and kick in terms of something with the renal system to maintain that. So the other thing about this is that while what we typically talk about is somebody that scenario of a heroin overdose where they're only breathing about 5 times a minute, check this out. You've got a patient you're on scene with a patient that has a history of COPD, and they're pumping along at about 32 times a minute. Would they be acidotic or alkaline? And I'm warning right now, I'm sending you on. What would you want to know?
Are they good respiration?
Yeah, why does that matter? So check this out. The idea that while they might be puffing along at 32 times a minute, if they're not moving the entire volume, what could be happening with their CO2? They're maintaining it, right? So that's the other way this can work. Next on. Increased ventilation decreases carbon dioxide and carbonic acid in the blood, thus increasing the pH. So the pH, PCO2, opposite directions in terms of the way it's traveled. This process helps to restore the normal pH in the acidotic state. So as we do something with the breathing portion of this, respiratory side of this, we're going to do something in terms of decreasing the CO2. That's going to result on this side of the pH coming back up again to some degree. Now, can we make all life better? In other words, if this pH was, let's say, 7.05, and we just increase the respiratory side, and we come back up into a normal range? Maybe and maybe not. Again, think about the heroin overdose that's in cardiac arrest. Bring it back. While we might reverse that and bring them back into a breathing thing, does it mean that the pH is going to return to a normal state? Maybe and maybe not. You don't know that without a blood gas machine. That's kind of the clinical.
And we're latent.
Yeah. All right, final system. So we talked about 2 systems. You understand that? Buffer system. The last of the big 3, if you will, is the renal system. So this takes a while for it to start to kick in. And again, to Will's question, it isn't like the kidneys just stop. But the idea is it takes a little bit for the kidneys to get the message in terms of kicking in and starting to get rid of this acidosis on board. How is it going to do that? How are the kidneys going to have an effect on this? Either retain fluid or kick fluid. In most cases, with an acidotic state, it's going to kick fluid. It's going to kick out those hydrogen ions. It's going to kick out the acidosis along the way. Okay?
How long does it take for the renal system to kick in?
Takes hours or even days for it to start to kick in adequately. But once it does, the good news is there's a good news and bad news thing. The bad news is it takes a while for it to start to kick in. The good news is if you want to know the system that's going to be the longest and the greatest effect, this right here. Because over a period of time, our respiratory system, if we get tired, can we breathe adequately? How many times have you been on scene where that person feels like they're taking their last breath? So the respiratory side is gone in terms of maintaining that. The one that's here is this. Who's going to be most affected by this system and not working well? Renal system, right? So again, you bring the disease process into the system that we're talking about. It has a bearing as to how well these systems are going to work along the way. Yeah? Yeah.
So they say that you really only need 1 kg of function correctly. If we've got a patient that only has 1 kg,
yeah.
Is this going to take a little bit?
So the answer to that is it depends on the disease state they're in. If they're completely healthy otherwise and everything else like that, no big deal. That kidney can compensate for everything else that's going on. But if that person with that 1 kidney also happens to be in renal failure or CHF or a cardiac history, then there's some problems going on. Does that make sense? Okay.
Would it, for those 3 different health situations, would it be the same if they had both of their kidneys? Or?
Yep, it really means the same thing. The body does this great job of compensating with just 1 kidney. That's the reason why we will. So when the pH falls in an acidotic state, the kidneys excrete hydrogen ions through urine. When the pH rises, the kidneys retain hydrogen ions. The bicarbonate ions are excreted. So just the opposite, depending on what's going on with your state. So Josh has kind of talked about, and I know that we kind of mentioned it throughout the break. But the idea that our body goes from aerobic state into an anaerobic state is the Krebs cycle. And to save my skull, we're not going into Krebs cycle, okay? To save yours as well, we're not going into Krebs cycle. But the bottom line is the Krebs cycle is all about going from this aerobic state into this anaerobic state. So the other thing that's going on throughout this entire state is we become more and more acidotic along the way. The body is going through this entire process of going from aerobic to anaerobic. The body does not function terribly well in an anaerobic state for any length of time. And so that's the other thing that's coming alongside of this. That's the other thing that's part of this that we won't get knee deep into. So when we talk about a respiratory versus metabolic process, we're either alkalotic or acidotic, depending on what's going on in terms of primary respiratory or primary metabolic abnormality. What am I talking about? Primary respiratory, primary metabolic.
And what's causing it?
Yeah. So primary respiratory, give me an example of that.
Just like something not breathing very fast.
Okay. Or let's say a COPD, even to make it easier, right? Okay. What about a primary metabolic? That gets a little bit tricky. Sepsis would be a great example of that. Absolutely. Sepsis is a good classic one. But how about DKA? How about aspirin overdose? How about some of the other overdoses along the way? They can have an effect on both the respiratory side and the metabolic side, depending on what the disease process is, depending on what the overdose is.
Would heroin fall under both of them?
So heroin initially would be an acidotic state, a respiratory acidotic state. Okay, we'll talk about that. So on this side, because we haven't talked a whole lot about it, what might be a reason for alkalosis? And I'll guarantee you've seen respiratory alkalosis.
Panic attacks.
Say again?
Panic attacks.
Yeah, panic attacks. So there, you get on scene, I can't feel my fingers, I can't feel my lips. The idea that they're huffing and puffing along about 60 times a minute, right? So what the body's going to do is that, have you ever seen those patients faint? They go into syncope episode. What's the body doing during that syncope episode? Recovering, right back into this right here. Make sense? They never ever thought about it that way before, but that's exactly what the body's doing.
Gary, is that kind of like what you said yesterday with giving oxygen to somebody with COPD? Is that you can kind of cause their body to shut down if you give them too much oxygen?
That's slightly outside of this, so I'll stay away from that question. Not that I don't want to answer that question, but I'll stay away from that because that's going to confuse this.
We actually had a patient a week ago who was having an attack like that, and her hands were curling and I was just curious, why does that happen specifically?
It's called muscle spasms. So the way that the body will kick in, because of this alkalotic state, the way the body will kick in is that it will switch over to this alkalosis, and so all the functions behind it, all this right here, this tingling and everything else like that, is a result of too much pH. Okay.
Alkalosis causes vasoconstriction.
Yep.
Which is why eventually the patient will actually pass out, but their brain isn't good enough. It's like a weird vicious cycle. So when you hyperventilate, you get alkalosis, which causes the vessels to constrict, which means you don't get enough oxygen to your blood tissue. And your brain says, I don't have enough oxygen, and you breathe faster, you get more oxygen. It makes you breathe faster, it makes you more alkalotic, it makes your vessels shrink more, and you get less oxygen to your brain. It's one of those positive feedback systems that basically can pass out, and then obviously everything returns to normal, so just slowly breathe back down. The same thing happens with your fingers. You get the alkalosis, obviously there's restriction of your vessels, and so all of a sudden you have these shifting issues to your fingers, and there's light and fluid.
So let me just give you a slide that actually sort of. I got home last night just in time to see my wife had on MCIS last night. And so it showed McGee, whose wife was pregnant, found out with ultrasound that they were having a form. Congratulations. Well, by the way, you're having twins. He fainted. And I thought about you all in the fact that is an example of alkalotic state. That's exactly what's going on in terms of body recouping itself. Okay.
How does
So is exactly what we're talking about. He started hyperventilating along the way, which then resulted in a syncopal episode, which then the body would. So back here, we kind of talked about respiratory as being the primary thing, okay? And we talked a wee bit about this as well. Let's go forward with that as well. If the primary process is metabolic in nature, there's too little or too much hydrogen ions in the blood, resulting in either a metabolic acidosis or metabolic alkalosis. So depending on what's going on. And we'll break these down here in just a couple minutes. When a metabolic problem develops, the body tends to respond by changing ventilation, either increasing it or slowing it down. It also will not only increase the rate, but it will also increase the amount of pipeline along the way. So when we talk about a DKA, you hear all the time about closed respiration, right? So what the body essentially is doing with closed respirations is it's trying to blow off CO2. It's the one and only game DKAs have along the way in terms of trying to do that all by itself. So the whole reason about closed respiration is the body compensating for this side right here. Right? Well, DKA is a metabolic thing in nature. It's a metabolic acidosis. We'll talk about that in a couple minutes. But the idea in terms of the body trying to take care of business, that's an example of that.
But it only goes to respiratory after its bicarb
Correct.
is depleted.
Correct. Correct. And so that's another reason why it takes 2 to 4 minutes for that to happen. Carbonic acid is doing its thing during that 2 to 4 minutes. Respiratory system is next to take care of that.
And then they're losing energy because they don't have the ability.
Yeah.
They're trying to blow it off. Don't have the energy.
So those patients, again, an example of DKA, those patients, their glucose is up here somewhere, right? The idea is not going to fall down this way all by itself. Insulin is the answer for that, right? So that's the other process. When a metabolic problem develops, the body tends to respond by changing ventilation, we talked about that, to at least partially compensate for metabolic change. Remember that while there is a primary problem, there's always a secondary problem. Key thing, okay? Now, I'm going to ask you that test question, but the idea in terms of every time that you're on scene, I don't care what it is, every time you're on scene, there's a primary problem and a secondary problem. And it might be only like a slant type thing in terms of shock state, but shock will always be associated with a disease process. Now, the hangnail is going to be shocked, but the idea is that you have somebody that with COPD exacerbation, they're going to have a shock state that kind of goes along with that. Does that make sense? And so, in terms of talking about this and dealing with it, in terms of doing this on the scale, the shock state is aerobic anabolism to anaerobic anabolism. So it goes back and forth. All right. So tell me what just worked during the last half hour. Whatever. So which one is the quickest? Upper system. What does it do? Okay. So it's going to take care of those hydrogen ions, right? And then it would dissolve into what? Carbonic acid. And it's exposed where? Primarily the lungs, although the kidneys again will play a part. Okay. What's the next system? Respiratory. What does it do? So it either increases or decreases. Be careful; it doesn't always increase, but increases or decreases depending on what the state is. Okay? So by increasing the respiratory rate, what does that have to do with this?
It increases the pH. Lowers CO2 levels.
The idea is going to take that CO2 and it's going to actually raise it to bring it back into a normal state. Okay. So, and because of that, the pH, as you talked about, Alex, the idea in terms of that, the pH will come back into somewhat of a normal state. The third system is what? Tell me about the renal system. Slowest, right? What does it do? Unfasten. What does it do? It excretes hydrogen or endogenous, depending on what's going on with the state, right? Okay? All right, so let's talk about 4 different acid-based arrangements that you need to know about. So this sometimes confuses others, and others do okay with this. Again, this is Gary's brain of trying to describe what we're talking about. So I think about some of these things with a first name, a middle name, and a last name. And I always look at the pH first. So in terms of the number, I always will start with the pH first. Although we're accustomed to looking at PCO2, I get that. But in terms of the blood gas, in terms of results from blood gas and everything else like that, I started the process by looking at pH. Why? What does that tell me? It tells me about whether or not we're talking about normal, we're talking about acidosis, or we're talking about alkalosis. Okay? So my process starts there in terms of knowing what that is. The second thing then is looking at the other side of that. I'm looking at whether or not there's a metabolic component to that, or is there a respiratory component, or is there both? Okay? And again, that's kind of the portion where some folks get sideways about this entire process. I'll see if I can't walk through that. So I'm looking at the pH, I'm then looking at the CO2 and the HCO3 to determine which way this is going. Okay? So by looking at that, then it gives me a clue in terms of whether or not we're talking about an acidosis versus alkalosis. It tells me whether or not we're talking about respiratory versus metabolic. And then again, the other one that will sometimes be confusing is whether or not this is compensated or uncompensated. And I'll try my very best, because this is the part that gets a lot of folks sideways. I'll try my best to try to talk about this. So HCO3 and pH will travel the highway in the same direction. So for instance, if you have a patient with a pH of 7.15, and this is a metabolic problem along the way, what would you expect the HCO3 to be? High or low? Low, right? If you have somebody with a pH of 7.45 and you believe it to be a metabolic problem, what's going to happen to HCO3? It's going to rise. It's going to rise above that 22, 26, or 22, 28, depending on which way you're looking at. So same thing in terms of PCO2. The difference being that in most cases, pH and PCO2 will travel in opposite sides of the highway. So if you're riding down I-90, pH will go westbound, PCO2 will go eastbound. They travel opposite directions. That being said, if somebody has a pH of 7.25, and you believe this to be a respiratory problem, which way, what's going to happen with the acidosis? It's going to be high or low? Absolutely, it's opposite direction. So they travel in opposite direction. That's one of the reasons that folks get kind of tied around the corner about this, because they travel in different directions. A change of 0.8 in a pH causes an opposite direction about 10 to PCO2. So the idea that if we have a pH of 7.35, and they're now a pH of 7.28, what would you expect the PCO2 to be? No, just the opposite. PCO2 travels in opposite direction. So normal PCO2 again is what? So what would you expect the PCO2 to be? Somewhere around 45 to 55. Okay. So it would go up by 10 based on this going down by 8. Okay. You need to know these numbers. I've shown this to you like 2 or 3 different times, but you need to know these numbers in terms of something else along the way.
So we're only able to look at end-tidal CO2.
Yeah.
We're not able to look at the pH or the one gas.
Yeah.
So
Your question is, why don't you know this, right?
Exactly. So I'll tell you what. If you just hang out for just a wee bit longer, I'm going to see if I can't answer that for you. Okay. All right.
Thank you for that.
Yeah. So everybody else is saying, thank you for saying.
But going back to that, we should be able to tell from our PCO2 if it's going up or down based on, we can have an idea of what the pH or the.
So that's one of the things we're talking about, folks, in terms of knowing what the disease process in your patient, as to what you're going to do with that, and what you can expect to be in terms of blood gas. Okay? That's part of the reason we're talking about this, or the fact we have.
About the difference of thinking of like 35.
Yeah, that's the start. That's the start of it. That's it right there. Absolutely.
So the way their HCT was one of your H's is
Hydrogen. Acidosis.
So how are you going to fix that when you're at a cardiac arrest? You have to know what's causing
Ventilation and your antibody. That's the reason.
I'm so glad we're going to get there.
All right, you all good with these numbers? So again, you understand in terms of, you understand both sides of this, right? So with a pH of less than 7.35, it's an acidotic state and it's not compensated, okay? If it's above 7.45, it's a base, it's not compensated. Now, here's a side that again, I'll try my best not to confuse it too much. But here's the other thing that happens is that if we're talking about a metabolic problem that creates this right here, and the respiratory side will start kicking in terms of going from a PCO2 of 35 to 45 down to a PCO2 all by itself. The body does this all by itself. PCO2 goes down to about 30. What's happening? The respiratory side is trying to compensate for the problem that's going on here. So when we talk about a compensated versus uncompensated, that's where it gets kind of sideways for some folks in terms of understanding that. We'll try our best to dive into that a little bit. So to your point,
I was hoping you'd say that. Yeah.
So here's why. Here's why we need to know it. There's 4 different states. We've already been talking about this, and so we're going to break out each one of these in terms of causes for it, what you can expect to do or see as far as in various states. Okay. Now, this is without the luxury of what Josh gets to see every day, and that is the blood gas machine before him. Okay. This is you looking at your patient, you knowing what's going on in terms of disease process along the way, and that way you would treat it based on where you think they're at with this right here.
Your real quick question: do you see like an iStat machine? Is that something you can bring in?
Yeah, I think so. I think once you start getting an iStat machine, you can have a better definition in terms of what this is. So my hope is that I know there's some agencies that's using that and have pretty good outcomes because of that. So, good question.
Unfortunately, we actually were having this discussion with the soup, and we're going to move to, unfortunately, Washington State. Every ambulance who has one has to register as a mobile.
Absolutely. So, did you all hear that? So that's the hang-up. Josh, to your question, that's the hang-up. So the current legislature, the current discussion that's going on, if you have an iStat, you're considered to be a lab. As a result of that, you have to go through all this accreditation process. You have to go through calibration on a daily basis. You have to go through a lot of things along the way to be part of that. There's some states that aren't at that in terms of defining that way. Washington just happens to be that Washington State.
And it's not just the company; it's every single ambulance of the company.
Right.
Even the non-iStat, or you're saying just?
No,
Just an iStat. That's using iStat. That's a good idea. Job security for somebody, right? All right. So starting with the common causes of probable reasons. On the left-hand side, we're talking about metabolic issues. We're talking about respiratory issues. We're talking about, in this case, acidosis. Okay. So very, very common respiratory issues that you know about is overdose. Specifically, narcotic overdoses that will slow the respiratory rate down. Those parts too long. Another common one is COPD. It can also be CHF. It can be CHF on the respiratory side. It can be CHF on the metabolic side. I'll let you finish writing and then we'll talk.
What is the shock state's response? It's not going to be a driver for that.
True, but what happens if the shock state gets worse over a period of time? Well, let's say the hypovolemic shock gets worse over a period of time. Are they going to maintain an aerobic metabolism or going to anaerobic metabolism? Which is going to make the acidosis worse. So it's always going to make it worse over a period of time. All right, left-hand side, metabolic, lactic acidosis. Lactic acidosis is going from the aerobic state, going from aerobic state into anaerobic state. So that Krebs cycle is kicking in terms of this whole thing. Common reasons for that would be shock, either being a primary problem or a secondary problem, depending on what's going on. So we're going to say cardiac arrest, and they come back out into a ROS. What kind of shock state are they going to be in? Probably cardiogenic shock, what did you say? Yeah. So the cardiogenic shock, you think they're going to be good to go, or do you think it's going to take a while for it to get back to normal state? The idea that it's a cardiac issue, that's part of that, but a shock state is going to make that much that worse. Hypoxia. So hypoxia is a respiratory thing. Why would it be over here in terms of this lactic acid?
It's without oxygen, the cells will start going into
Thank you.
anaerobic respiration.
So is it a respiratory problem as well? Yeah, it's a respiratory problem as well, but the thing that kind of drives it is this right here on this metabolic side. Cyanide. So firefighters, you've been doing internal structure. You come out, you sit down, you do rehab, and oh, by the way, you took about 5 minutes worth of versus smoking side. The possibility of cyanide overdose is on this side right here.